Making this video would normally be beneath a sigma male of my stature, but when going through my fractional calculus material, I realized that I didn't really have a choice. So this lesson's going to be about the beta function, also known as the Euler integral of the first kind. Now, the beta function isn't like the betas who think that being afraid of mathematics somehow makes them cool, or that taking bird courses and doing yoga for 4 years properly equips them to handle the rigors of medical school. Instead, the beta function has legitimate uses in calculus and different areas of physics. Now, the beta function is denoted by a capital B, and it's a function of two complex numbers z1 and z2, with the proviso that the real parts of z1 and z2 are positive. It's defined by the following integral involving z1 and z2. The integral from 0 to 1 of t to the z1 minus 1 times 1 minus t to the z2 minus 1 with respect to t, and t is just a dummy parameter here. And B also has some interesting and important properties. The first is the symmetry property, which says that the beta of z1 and z2 is the same as the beta of z2 and z1. The proof of this is pretty simple. We know that by definition, the beta of z1 and z2 is the following. Now, to prove the symmetry property, we'll make a u substitution and let u equal 1 minus t. In that case, t is just 1 minus u and du is just negative dt. The limits of integration this time switch from 1 to 0 when we integrate with respect to u, as opposed to 0 to 1. Now, if we make these substitutions to our integral, this is what we get. And since we've got a negative sign with the du, we can actually use it to flip the limits of our integration and end up with the following. And does this look familiar? Well, it should, because this is just the definition of the beta function of z2 and z1. We've got the power involving z2 attached to the variable u, and the power involving z1 attached to the variable 1 minus u. This is just the beta function of z2, z1. So we've shown that the beta function of z1 and z2 is the same as the beta function of z2 and z1, making the beta function a symmetric function. The next property we're going to talk about is the relationship between the beta function and the gamma function. Specifically, the beta function of z1 and z2 is the product of the individual gamma functions of z1 and z2 divided by the gamma function of z1 plus z2. Let's now prove this property. We'll start by recalling the definition of the gamma function, which is that the gamma function of a complex number z is given by this integral from 0 to infinity of e to the negative t times t to the z minus 1. Using this definition, we can start our proof of this beta function property. We'll begin by taking the product of the gamma function of two complex numbers z1 and z2, the numerator of the property we're trying to prove. And using the definition of the gamma function, this is what that product turns out as. Notice that I've written the variables being integrated in these two integrals as different variables u and v. The idea behind this is that we eventually want to combine these two integrals and get a double integral like so, where I've already combined the powers on the two exponentials to get one single exponential. But this is where things get a bit weird. Instead of doing a single variable substitution to simplify this integral, we'll be doing a double variable substitution. So this u plus v in the exponential power will represent with the variable s, and the variable t will write as the ratio of u and u plus v. You'll notice from these relationships that if I multiply s and t, I'll just get u, because u plus v's cancel from the numerator and denominator. You'll also notice that since u is the product of s and t, I can substitute that in the equation for s to isolate v in terms of s and t, so I get v equaling the product of s and 1 minus t. So let's use the equations for s and t to find our new limits when we make this variable substitution. When u is 0, then we know that t equals 0 regardless of the non-zero value of v, while s is just equal to v. When v is 0, then t just equals 1 as long as u is non-zero, and s just equals u. Similarly, when either u or v approach infinity, s also approaches infinity. T approaches 0 if only v approaches infinity, and it approaches 1 if only u approaches infinity. So we can see from these computations that the limits to put on our s are 0 and infinity, the maximum and minimum possible values of s in this parametric setup. And on the other hand, the limits to put on our t are 0 and 1, the minimum and maximum possible values of t. Now, the other thing we need to do when making this substitution to s and t is to convert the du dv in our original integral to an expression that involves ds and dt. And the way to do this is to use the conversion formula with the Jacobian of this variable change or variable transformation. Recall that the Jacobian is the determinant of the Jacobian matrix, and we can use this Jacobian to get the area element in the new variables s and t. Note that we're taking the absolute value of the Jacobian here. Recall also that the Jacobian matrix of this change in variables is given by the following, with its elements being the partial derivatives of u and v in s and t. If we use our equations for u and v in terms of s and t, we can easily get these partial derivatives, which turn out to be the following. And so now that we have the Jacobian matrix, if we take the determinant of this matrix, so the AD minus BC, this is what we'll get. And if we simplify, we find that the determinant of the Jacobian matrix, the Jacobian, is just the negative s. And since s is a non-negative number because it varies from 0 to infinity in our integral, negative s is a non-positive number, so if we want the absolute value of the Jacobian, we need to change the negative s, a non-positive number, to the simple s, which is a non-negative number. So now we have the new limits of integration, we have the area element, and we have the expressions for the new variables s and t in terms of the old variables u and v. If we go back to our original u and v integral and make all of these substitutions, this is what we'll get to get a double integral in terms of s and t. Let's now split up the terms involving s and t, because our goal here is to eventually separate the integrals in s and t once more. And now that we have two separated expressions in the variables s and t, we can separate out the integrals again, like so. If we combine the powers on the s terms in the first integral, we get the following expression. Now have a look at this first integral. Does it look familiar? It should, because if we go back to our definition of the gamma function, we can see that this is just the gamma function of z1 plus z2. The only difference here is that we have s being integrated instead of t, but this doesn't actually affect our final answer. It's still the gamma function. Meanwhile, this second integral is straight up the definition of the beta function of z1 and z2. So we've shown that the gamma function of z1 times the gamma function of z2 equals the gamma function of z1 plus z2 times the beta function of z1 and z2. So if we isolate the beta function term, we get this ratio. So we've proved this relationship between the beta function and gamma function, and this relationship is going to come in handy for our fractional calculus videos, so stay tuned for those. A couple of other things I'll mention to conclude this video. Just like how we wrote the beta function for two variables, we can also write the beta function for multiple variables, just by extending this gamma function formula. And this is what we would call our multivariate beta function. And the other thing I'll mention is the binomial theorem, the expansion of x plus y to the n, which is given by the following formula, if you recall. Now, the two variables in a summation being raised to slightly different powers is pretty similar to the beta function, except with the beta function we have an integration instead of a summation. And that's why many of the properties of the beta function actually resemble the properties of binomial coefficients, the n choose k in the binomial theorem. I won't go over these properties here, but I'll mention the resemblance just to give you a better way to relate the beta function to something you might already be familiar with. Anyway, that should do it for this lesson. I'd like to thank the following patrons, and if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan, signing out.